in the iterative least squares or steepest descent that we derived, we did something a little funny. And let me just start by pointing that out. Quadratic error surface, starting condition, we move down, we move perpendicular, we move down, we move perpendicular, and so on and so forth until we get the minimum. And what do you notice about this is that there's an inefficiency here in some ways, because notice that I started up here and I moved down and I stopped when I hit the minimum. That was by definition. And then I moved over. And then notice, because all successive steps in this iterative process are going to be perpendicular, the third step is going to be the same direction as the first step. And the fourth step is going to be the same direction as the second step. That's by definition. It has to be that way. And so here's an obvious question. If you knew you had to get all the way down here in this direction, why did I cut the corner? Why didn't I just keep going and then do this and then keep going? So there's an inefficiency here. And why do we care about that inefficiency? Because it's iterative. Every time we take a step, we have to do some calculations. And it seems like this is not as efficient as it could be. So, for example, could I have just done this? Could I have started at this point and gone down a little bit further and in fact gone uphill a little bit, and then notice this is no longer perpendicular here, and then just gone over to the minimum? Yeah. So this is called conjugate gradient descent. And what's really beautiful, so with steepest descent, you have to do a bunch of iterations until you hit a threshold. And you create some arbitrary threshold. With conjugate gradient descent, you are guaranteed to converge in the number of steps that is equal to the number of unknowns. Here we're in a two-dimensional space, 2 steps. Any point in this space, there are 2 directions and 2 step sizes that will guarantee to get me to a minimum. If we're in a 3-dimensional space, there are 3 steps that will get me to the minimum, and that is provably so, and is the number of unknowns. Now here's the good news. The good news is that the update rule is basically the same. On the I plus 1 iteration, take the previous estimate, this one right here, pick a direction, and move by some step size. Here's the bad news. Figuring out these directions and step sizes is a little bit, in fact, a lot more complicated, in part because we don't have this nice perpendicular constraint here. And so I'm not going to go through the derivation. If you're curious, there are many, many very nice papers. We'll link one in the course website to conjugate gradient descent. I'm not going to derive it because I think we've gone through enough pain and suffering to get to steepest descent. But I am going to give you the code for it just so you can see it. And I'll go through this fairly quickly since we didn't derive it. Same game as before, generate some data. Here's my A and B matrix. Those hasn't changed. Pick a random point UI and define now, I need 2 things. I need this D sub I and R sub I. R sub I was this, actually this looks very familiar. B minus A UI, that's the direction of the negative gradient. And Ri on the first iteration is the same as Di, but these are going to change on subsequent iterations. By the way, that makes sense because that first step, is the direction's exactly the same, but the step size is going to be different. Now, same for loop, same while loop, an infinite while loop that's going to keep going. I actually could have done this as a for loop because I know exactly how many steps there are, but I'm going to do this this way anyway. I'm going to define A sub I, that's the step size, and then U sub j on the first iteration is just this thing right here. This is a slightly different formulation from before. You've got the Ri on the numerator, but you've got the D sub I on the denominator. So the step size is going to be calculated a little bit differently, which is what you expect, because we're going to overshoot, and there's how we compute the overshoot. And then we compute the R, the B, and the D that we need for the next iteration. And I've got a catch here for the stopping condition, although I actually didn't need that because I'm guaranteed to stop after 2 iterations. So this is just an artifact that I used the previous code. With this code, I could have done this just simply forcing it to be 2 steps, and I get to the minimum guaranteed. And the only difference is I've got a slightly more complicated denominator here, and I've got to lug around an extra term here in computing the step size, but the direction is computed in a similar way. So that's sort of cool. So now we have steepest descent and we have conjugate descent. And the only difference here are the number of iterations and how you move through the space and the calculations that are involved. Now, one thing I haven't done yet is gone back to where we started. We started with least squares is really expensive, big O of n cubed, when we have very, very big matrices. And now we should go back and look at steepest descent and conjugate gradient to determine, well, have we done any better? And we'll do that when we come back.